Hello and welcome to Team VLSI. Today we are going to discuss about the SPEF file, that is Standard Parasitic Extraction Format file. In physical design, under the series various files in the physical design. So please do like this video and subscribe our channel. Our channel is youtube.com/teamvlsi, or you can search Team VLSI on Google or YouTube. So in this series, we have decided to discuss all these files, and till now we have completed up to SPEF file in 6 sessions. Today we are going to discuss about the SPEF file. So let's begin. So first of all, highlights of this session. We will first discuss about the basic introduction of SPEF file format, followed by various sections and attributes of SPEF file. Then we'll see an example and try to understand the SPEF file using a schematic. And at final we will see the usage and generation of SPEF file. So first, introduction. So basics of SPEF file. SPEF stands for Standard Parasitic Exchange Format. SPEF is an IEEE standard for representing parasitic data of a wire in a chip in ASCII format, and latest version is 1481/2009 IEEE standard. So every real wire has parasitic resistance and capacitance that are captured in SPEF file. So in your design, every interconnects has some parasitic resistance and capacitance value that will be extracted and captured in your SPEF file. So SPEF file is a standard medium to pass the parasitic information between various tools during any stage of design process. SPEF file is mainly used for delay calculation by STA tools, but its application is not limited to only STA So SPEF file is extracted after routing in PNR flow to get the accurate calculation of the delay for STA and other analysis like IR drop. So this was the basic introduction of the SPEF file. Now we will move to the SPEF file section. So an SPEF file will have mainly 4 sections, and these sections are: first is header section, second is a name map section, third is your top level port section, and fourth is parasitic description section. So we will see one by one all these sections. But before that, we have a keyword. Generally, the SPEF keyword generally starts with asterisk, like asterisk d_net, asterisk name_map, asterisk r_unit, etc. And double backslash is used for comment any line in your SPEF file. So first section is our header section. So let's see so header section mainly contains following information. First, it's SPEF version, and right side you can see here it's the exact format how in your SPEF file it's written. So it starts with the asterisk SPEF followed by IEEE 1481-1999. So this is the version of SPEF. Then comes the design name, and it starts with asterisk design followed by your design name, and then date of generation. It starts with the asterisk date followed by the time, then day, then month, then date, followed by year. Then tool vendor's name. It starts with asterisk vendor followed by your vendor, like it could be your Cadence, Synopsys, or any other vendor. Then parasitic extraction tool name, then it contains parasitic extraction tool name. So it starts with the asterisk program followed by your tool name. It could be either Qantas, Star, RC, or Caliber, or any other tools. Then version of tool starts with the asterisk version followed by your tool version. Then design flow, asterisk design flow. Then divider is generally represented by the backslash. Then hierarchy delimiter, it is generally represented by the colon. Then bus delimiter is generally represented by the square bracket. Then units, in unit section we have time unit, capacitance unit, resistance unit, and inductance unit. Time unit could be represented as 1 picosecond, capacitance unit could be represented as 1 femtofarad, resistance unit could be 1 kilo ohm, inductance unit could be 1 micro ohm, Henry. With this, the header section is complete. So generally there are 14 lines in this header section. So now we will move to the next section, and next section is the name map section. So name map section starts with the keyword asterisk name map. Asterisk I have missed here. So this is an optional section and used to reduce the file size by mapping the long names into shorter numbers preceded by the asterisk. So for example, see, it's one node is naming node underscore name underscore 1. It could be a longer name, but in name map we can provide a number preceded by a asterisk. So basically we can represent this longer name by a number. So this is the example, like you can see here. This is the long name, like top underscore buff g clock underscore 3 underscore pin underscore g underscore 1. We can if we in name section, if we declare it like asterisk 511 followed by the name of your nodes, then later we can refer this long name by asterisk 512 or 511, whatever it is. So it's underscore 3, it's 512. Okay. So typically short names such names such as pin A will not be mapped, as mapping would not reduce the file size. So generally we for a longer map it is very useful. Shorter name we can either skip, like if your pin name is only A, then we can skip it. So next section is port section. In port section it starts with the keyword asterisk ports. Here is the general syntax. So it's ports number, asterisk, and 1 it's the port's name, which we have defined in the name section, followed by either O or I or B. O for the output ports, I for input ports, and B for bidirectional. So here you can see the example, like asterisk 509 is the input port, asterisk 510 is the output port, asterisk 515 is a bidirectional port. Next is our parasitic section. This is the most important section of your SPEF file. Here all the parasitic value is written in this section only. So try to understand this section very carefully. If you can't get the exact things here, don't worry. We will discuss an example. I think you will get the things more clearly in that section. So let's start the parasitic section. So each extracted net will have a dnet section. Okay. So dnet section consists of following subsection. again. We have under the DNet line, we have a connection section, capacitance section, resistance section, and section. Okay, so here is an example. You can see this is the complete parasitic section. So parasitic section starts with the DNet section, then there is a connection section, then there is a capacitance section, then there is a resistance section, and finally it's AND. So asterisk AND is the indication of the end of parasitic section. So we will see all these things in details. For here, the renet line tells that the net name and the total capacitance of the net. So here basically three parts. First is strict DNet, followed by your net's name. Here it is written complete name. It could be either its short name like asterisk followed by some number. Then this is the total capacitance of this net. The total capacitance will be sum of all the capacitance in the cap section. Because of so you can see here in cap section there are three capacitance, and sum of these three numbers will come here. How it comes, why this is the sum of all these three, I will discuss when I will discuss the example. So next is our connection section. In connection sections has list of pins connected to the net. This section could start. This section will start with a keyword asterisk connect CONN. Then the entry, its general syntax is either asterisk I or asterisk P. Asterisk I is used for internal pin and asterisk P is for external pins like top level ports. So first asterisk I, then pin names come here. It could be shortened name. Then direction of the pin, and then asterisk C followed by the coordinates of your pin, then loading or driving information. So direction could be either input, output, or bidirection. Here is the example. You can see this section starts with the asterisk CONN. Then all these three here are the internal pins. So it starts with the asterisk I followed by the pin name, then its direction. First two are inputs and last one is output. And then asterisk C followed by a number. So asterisk C gives the XY coordinate of pin in layout. So it's the location of your pin. Then followed by either asterisk L or asterisk D. If your pin is input, you can see here, then asterisk L will come, and asterisk L gives the load capacitance of the input pin, and asterisk D gives the driving cell type for an output pin. So for output pins, asterisk D will come, and for the input pin, asterisk L will come. That is your load capacitance. So with this, we will move to the resistance capacitance section. The asterisk cap section provides detailed capacitance information of the net. So there are two types of entry in the cap section. First is capacitor lump to ground, and second is coupled capacitors. So capacitor lump to ground has three fields. First is an identifying number, second is a node name, third is the capacitance value of the node. So you can see here, first is this is your capacitance section. So this section starts with asterisk cap keyword. Then first is your identifying number, Second is your node name. Here it is complete node name is written here. It could be either shortened name followed by a number. This number is your capacitance value, and this is an example of your lumped capacitance. Second type of capacitance is your coupling capacitance. Has 4 fields. First is identifying number, and there will be 2 nodes name instead of 1. So why this type of capacitance is between the 2 nodes. So starting nodes and end nodes are there, then followed by your capacitance value. So in second line you can see here identifying number 2, there are 2 nodes, okay, and followed by a capacitance value. So if a net N1 has coupled with net N2, then coupling capacitor will listed in the strict cap section of each net. So if capacitor is coming between 2 nets, then this capacitor's value will come in the parasitic section of the both nets. Okay, so now we will see the resistance section. So the strict resistance section provides resistance network for the net, and there are 4 fields in the resistance section. First is your identifying number. Here is the example. So this section starts with the keyword *res. Then the first field is your identifying number. Second is your node's name, and finally the value of your resistance. So there are 2 nodes. Necessarily there are 2 nodes between which the resistance is connected. So the first node is here, second node is here, and between them this value of capacitance is connected. So the strict AND is used to denote the AND of parasitic section for the DNet section. Okay. In the above discussion, we have discussed a single resistance or capacitance value, but it is up to the parasitic extraction and delay calculation flow to decide which corners this value represents. So SPEF also allows for mean, typical, max values to be reported. Example, here this is the identifying number followed by a node name having 3 capacitance value. This is the mean value, this is the typical value, and this is the max value. Okay, so now we will see an example of SPEF file. So I have INP2 input 2 ports here, which is coming from your top level to a AND gate, and this input port is connected to AND gate through a net, and this net has this much of parasitics. So we will see how tool will write these things in your SPEF file. I have given all these capacitance resistance values here, and unit for capacitance is your femtofarad, and for resistance is kilo ohm, as you will define in the header section. So this is the header section of your SPEF file. I have already discussed this file, and this does not contain any parasitics value. So it will be as usual we have discussed in previous slides. So come to the parasitic parts. So in parasitic section, first is your name map. Here we have port INP2, and INP2 is shortened by the asterisk 1 here. So asterisk 1, we can use asterisk 1 to refer the INP2 later in this file. Then you can see here asterisk dnet followed by asterisk 1. So this is the net name, which is again it's INP2, and 2.0 is representing the total capacitance, total load capacitance of this net, total capacitance of this net. So here you can see all these 4 capacitance are the lump capacitance to the ground. So we can imagine a single capacitance is equivalent to parallel capacitance of all these 4. So that single capacitance value will be the sum of all these 4 values. So if you add all these 4 values, it will come to 2 femtofarad. So 2 femtofarad will be total load capacitance for this net. Second part is your connection. So connections, first entry is here asterisk p. Why asterisk p? Asterisk p is used for external ports or top level ports. So here we assume here our input 2 port is coming from the top level, that's why asterisk p is used here. Followed by the name of the p, we have shortened it by asterisk 1, and its direction. So this is your input p, so I is used for that. Second is asterisk I. Asterisk I is for the internal pins, followed by the name. So its name for this B pins, its name will be U1 colon B. U1 is your gate's name, followed by B its a pin name, and its direction is input, so I is used for that. Next part will come the capacitance section, and see the capacitance section. First come to this node. Identifying number is 1, and for this node name is asterisk 1 representing INP2. Then this node is having capacitance value is C1, and C1 is 0.2, so 0.2 is here. Then come to the next node. Next node is INP2 colon 1. It can be represented as asterisk 1 colon 1. So you can see here asterisk 1 colon 1 is representing this node, and its capacitance value is C2. C2 is equal to 0.5 femtofarad, so 0.5 is here. Similarly for node 3, asterisk 1 colon 2, and its capacitance value is C3. C3 is 0.4, so 0.4 is here. And finally we have a node. This node's name is B, so it will be written as U1 colon B. U1 colon B, and its capacitance is C4, and C4's value is 0.9, so 0.9 is here. So hope all these things are clear to you. Now move to the resistance section. So for resistance section, you can see here R1 is connected between the node INP2 and INP2 colon 1. And this is identifying number 1, and these two nodes are, first is asterisk 1 and second is asterisk 1 colon 1, and the resistance is connected between these two is R1, and R1 value is 1.4, so 1.4 kilo ohm is here. Similarly, for come to this pair of nodes, this is your asterisk 1 colon 1, and this is your asterisk 1 colon 2, and the capacitance is R2's value is 1.5. So asterisk 1 colon 1, asterisk 1 colon 2, and value is 1.5. Similarly, for this is node is asterisk 1 colon 2, and this node name is U1 colon B, and the value is R3 is 1.6. So resistance section is completed. Now this is asterisk and is indication of ending the parasitic section. Hope you have understand this example. So this example, how SPF file is written. This example is one of the simplest way I have used, but in real SPF file, the things are more complex. Now we'll discuss some important notes. A similar file with SPF file is called SDF file. It's a cadence design system standard file for defining the netlist parasitic. So usage of the SPF file, basically SPF file is basically used for static timing analysis. In Innova's tool, when we call time design to report the timing, extraction is performed automatically in background of the tool. Next, for IR analysis, SPF file is needed to get information of RC value of nets. Now, ED tools which are used for extracting the SPF, these are the ED tools. Quantus from the cadence design system, Star RC is from Synopsys, Caliber from the Mentor Graphics, and now it's Siemens, and ANSYS Q3D extractor is from ANSYS. So these are the popular tools which industry uses for SPF generation. With this, I am concluding this session here. Thank you for watching this session. Please do like this video and subscribe our channel. Thank you for watching.